Now this molecule is called Pinacol. This is 1,2-diol. So this is an example of 1,2-diol. Now what will be the product if this compound is treated with H2SO4? Generally concentrated H2SO4 is taken. So we have to write major product for this reaction. So in the first step, alcohol gets protonated. So H2SO4 can donate a H plus because it is acid. So alcohol gets protonated. In the next step, we can lose one molecule of water. Now this carbocation can rearrange to form a more stable carbocation. So if I shift this methyl group here, that is rearrangement of carbocation by methyl shift. So this is methyl shift. So if I do methyl shift, I will have this product. This is basically rearrangement of carbocation. And this carbocation is particularly very stable because of the resonating structure. So one of the resonating structure for this compound is this one, and this is very stable because in this case octet of each atom is complete. So you see octet of oxygen and carbon is complete, but in this case octet of carbon is not complete. So this resonating structure is very stable, and reason is octet of each atom is complete. So in the next step, if I consider this resonating structure, we can simply lose one H plus to get the final product. So we will have this as the final product, and this is called Pinacolone. So this final product is called Pinacolone, and that's why this rearrangement is called Pinacol, the initial product, initial reactant, and the final product is Pinacolone. So reaction is called Pinacol Pinacolone rearrangement. So let us try this problem. So we have two methyl group attached to this carbon, one OH. This carbon contains two hydrogen and one OH. Once again, this is example of 1,2-diol. Now if this is treated with H2SO4 and generally concentrated H2SO4 is taken, what will be the major product in this reaction? This is again Pinacol Pinacolone reaction. Now in the first step we have to lose H2O to generate the carbocation. If I lose this OH, we'll get a primary carbocation. Now if I lose this OH, we will have a tertiary carbocation. So in the first step, the carbocation that is more stable is generally formed. So this carbocation will not be formed because this is a 1 degree carbocation. So this carbocation is not formed. This is because this is 1 degree carbocation. Now this is formed. Now the next step, we can do a hydride shift. So we have methyl carbon, methyl, and we will have hydrogen, OH, hydrogen. Now the next step, we can lose H plus from here to get the final product. And in this case, final product is an aldehyde. So this contains a aldehyde functional group. So this is a aldehyde. If you see the previous one, the final product is a ketone. So final product is a ketone. So depending upon the situation, the final product can be aldehyde or ketone. Now let us try this problem. So once again, this is a 1,2 diol, and this is unsymmetrical 1,2 diol, because on carbon number 1 we have different groups and carbon number 2 we have different groups. So this is a case of unsymmetrical 1,2 diol. Now if this compound is treated with H2SO4, what will be the major product? And concentrated H2SO4 is taken. Now you may remember in the first step, we generate the more stable carbocation. So initially, we have to generate more stable carbocation. So this can be done if I lose OH from here, because in that case carbocation is resonance stabilized by the benzene ring. Basically here is we have OH group. So this is OH. So by mistake I have written Me. And the next step we can do a methyl shift. And the next step we can lose H plus to generate an ketone. So final product in this case is a ketone. C double bond O pH. So final product is a ketone. Now let us try this problem. So this is a case of 1,2 diol, and this time symmetrical. So this is a symmetrical 1,2 diol. Now if this is treated with H2SO4 concentrated, what will be the major product? Now whenever we have symmetrical diol, formation of carbocation is not a problem. We can either form from this carbon or we can form at this carbon. Both will give the same carbocation. So in this case, symmetrical 1,2 diol, formation of carbocation is not an issue. So in the first step, we can generate a carbocation. Now in the next step, we can do a methyl shift, alkyl shift. So we need alkyl shift. And this time alkyl shift, we can shift this group here. That is, we are having a ring expansion. So we can write this is carbon number 1 and this carbon is connected to this carbon 2. So we are breaking this bond and we are connecting these two carbon. This is 3, 4, 5, 6. So this side we have a 5-membered ring. And this side we have a 6-membered ring, and this carbon is common in the two rings. So let us number this carbon 1, 2, 3, 4, 5, 6. Carbon number 6 will have an OH group, and there is a loss of bond at carbon number 6, so it will have a plus charge. So we have a 6-membered ring, and then we have a 5-membered ring. In the next step, we can lose H plus to generate ketone. So this is the final product we have. Now let us try this problem. This is slightly tricky. So we have an OH group here. This carbon also has OH group. Now H2SO4, we have to write major product. Now this is a case of unsymmetrical 1,2-diol. Now in this case, we can form carbocation from here, or we can also form carbocation from here. Let us try. So this is one possibility. Another possibility we have this possibility. Now this is a 3-degree carbocation, and this carbocation is also 3 degree. But this carbocation is less stable. Reason is, this carbocation is inside the ring. One reason is, carbocation is in the ring. Another reason for less stability is, this has 4 hydrogen for hyperconjugation. So 4 hydrogen in hyperconjugation. Now if you see this carbocation, this has 3 plus 3, 6 hydrogen for hyperconjugation. And this carbocation does not include a ring. So this is more a stable carbocation. So this carbocation is more a stable carbocation. So now we have this carbocation formed. Now in the next step we can do alkyl shift, and this time alkyl shift will generate ring expansion. So what we will have, this carbon and this carbon is connected. So we have 5-membered ring, and carbon number 1 will have 2 CH3 group. Carbon number 5 has a OH group. So this is 1, 2, 3, 4, 5, and carbon number 5 will also have positive charge. So in the next step, we can simply lose H plus to get the final product. So we have this carbocation, and we can lose H plus. So we'll have this carbocation as the final product. Basically this ketone, not carbocation. So this is the ketone, that is the final product. So important point we said in this tutorial, whenever you have Pinacol Pinacolone rearrangement, this is only given by 1,2-diol. You have to see two things, whether the diol is symmetrical or unsymmetrical. When you have symmetrical diol, formation of carbocation is not an issue. When you have unsymmetrical diol, you have to form the carbocation that is more stable. In the next step, you can do hydride shift, methyl shift, or alkyl shift, and this can also be done by ring expansion. And finally, you have to lose H plus to generate aldehyde or ketone. So this is the mechanism for Pinacol Pinacolone rearrangement.